Good morning, everyone. Welcome to the Planetary Sample Science Seminar Series. It's hosted by the CASA Moon team here at UNM, Survey Central, the UNM Grand Challenge, the Institute of Meteoritics, LPI, the Lunar Planetary Institute, and then RASL with Johns Hopkins and APL. And so, real quick, just wanted to spotlight that next week we'll have Alexander King from Purdue University. And so, focusing a little bit on the regolith here, so nanoscale storage of solar wind volatiles and their retention on the lunar surface. So for today, we'll be introducing Chip Shearer. So he's a research scientist here at UNM. He's the head of the CASA Moon team and stuff. And so, Chip, ready to go ahead and take us away?
Thank you, Quentin. And where's the?
Oh, the clicker's on the.
Okay, great.
Yeah.
I'm really pleased to be here for the first kickoff for our second semester of the Planetary Sample Science Seminar series. And what I'm really going to do is present an outline what we were essentially doing at the request of NASA headquarters, Jack Bleacher, essentially looking at what's the importance of sample return for the exploration of the moon beyond, primarily focusing on the Artemis mission. And again, also focusing primarily on engineers and what engineers need to know about samples and the importance of samples. Because in some cases, an engineer may think, well, we picked up a sample on the surface during Artemis 3, that task is done. We can now go on and do other sorts of things. So this was kind of geared for that group. And what I would really like to do is thank those individuals who were intimately involved in putting this together. Steve Parman from Lunascope of Brown University. And then we had the Survey Sample Science Focus Group with Carolyn, James, Tony, Thomas, and Michelle, all involved in aspects of this analysis that we did for NASA headquarters. And I just really want to show you this image. This is a really cool image. It's from the Forest Littoral Valley taken during Apollo 17. And this is the famous Shorty crater that you see here. And what you'll see in the upper rim of Shorty crater, if you look closely, just right in this area, you'll see the soil's a little orange. That's the famous orange soil collected at Station 4 at Shorty crater. What I'd like to do is, just in terms of a general outline, this is the way we presented it to Jake and the exploration group at NASA headquarters. Just the legacy of the Apollo program, lessons learned from samples, both from Apollo and the subsequent ANSA initiative, and then look at the Artemis program and in terms of samples for understanding the moon at this fairly unique environment on the lunar surface. And Steve Harmon, his whole family is engineers. And so he interviewed them in terms of producing these sorts of questions that engineers would ask for Artemis. Why do we need to collect samples? Aren't all rocks the same? What? I know this is kind of funny, but again, when you're planning a mission from an engineering perspective, these are the questions you ask. What can we do with return samples that we can't do on the moon or by remote sensing? Why do we need to bring them back? How much sample do we need to collect? Is it just only one sample? Is it, 0.5 grams of material and then the mission's done and we come back? Can I scoop a sample off the surface? Or do I need to drill down to get regolith deeper than that surface sample? Do we need humans to collect samples, or can rovers do it just as well? And then finally, Do we have to transport and store the samples in some special way when you bring them from the moon, collect them on the moon, and bring them to Earth? So these are, in this presentation, hopefully you'll see in some cases, I'm gearing to provide at least some answers to these questions. And I'll provide the answers at the end, or some of the answers. Let's go ahead and again, lessons learned from Apollo. From Apollo, we had 6 sample sites, 382 kilograms of mass collected, 2,196 samples were collected, and from a wide range of rocks, soil, ores, and they are usually in pristine condition. And because we had humans on the surface operating as geologists, we have a really exquisite geological context, and that's been even more improved with remote sensing and placing these into a local geological context and a much broader geological context. But again, engineers and people who aren't familiar with the moon could say, well, we've had a number of lunar missions by humans. We had the lunar missions, the Soviet Union, and of course we have the Chinese missions, at least right now, 2 sample return missions. And this diagram, the 2 diagrams to your left, just illustrate on the surface of the moon where those samples came from. Again, they're primarily in and adjacent to what's called the Procellarum Creek terrain. And this is somewhat unusual in which this has a lot of Mare basalts associated with impact basins, and this is fairly high thorium. So it's a fairly unusual place compared to the rest of the moon. Also, if you really look at the surface area of the moon, it's approximately 14.6 million square miles in terms of total area. And if you look kind of at the North American continent, plus Central America, plus South America, it's approximately that, a little over 16 million square miles. If we go ahead and place the Apollo missions within the context of that landmass, you can see where they would lie if they were centered around the eastern United States. 12, 14, 11, 15, 16, 17, all into this area. So as you can imagine, what can you do with geology if you went only to these spots? You never go to see the Canadian Shield. You never go to the oceans and subduction zones. You probably see the Rockies, but you don't sample the Rockies. You never sample the Andes. So this kind of just puts that in the context that there is so much unexplored and unsampled moon. Some of the Apollo samples are fairly large. This just lists 3 of them right here. 61016 called Old Muley. It's it's almost 12 kilograms. 15555 Great Scott, about 9.6 kilograms. And then of course Big Bertha, 14321, which is a little over 9 kilograms. And so these are fairly large samples that were collected, and they range from breccias to Mare basalt. 15555 is a Mare basalt collected on an Apollo 15 site. The Apollo program also illustrated how human capabilities improve your ability to collect samples on the surface of the moon. To the left, upper left, you have EVA hours that were spent on the lunar surface, and you can see that increased dramatically from 11 to 17. And then if you look at EVA distance, again, from 11 to 15 to 16 and 17, you were able to traverse a much greater distance. and sample over a much more diverse area and collect diverse samples. And this is primarily what you're seeing there in terms of EVA hours, EVA distance, and eventually sample mass on the bottom left really just illustrates that with mobility offers a lot more capability. And from the yellow and green to the purple, you essentially go from mobility just by what the astronauts are walking to actually rovers that the astronauts can travel, and these are essentially the J missions. David Crane from the LPI, when we were discussing 20 years ago, the sample mass that humans needed to bring back, he put together this diagram in terms of EVA duration versus sample mass. And there was, for the Apollo samples, a real positive correlation between the EVA duration and the amount of time on the surface of the moon and the sample mass that you can bring back. Ideally, with regards to some of the Artemis missions in the future, Artemis 4, 5, 6, 7, the EVA duration is going to be far more than Apollo 16 and 17, but the capability of those landers right now has the capability of returning upwards of 100 kilograms of samples. So there's a real issue there, again, that petrologists and lunar geochemists are always battling. The Apollo program had a variety of different sample tools. Hopefully that some of these are well proven and they will be utilized during Artemis. Obviously a geological hammer, small scoops, rakes that one can rake the regolith and pull out little samples of the regolith that are of a particular size, rover soil sampler, in which driving on the lunar surface, you have this little device that you can, without getting out of the rover, you can just reach down and grab a sample. Tongs, what's called a soil, contact soil sampling device. And this was designed primarily to collect this material on the only upper surface, double and single drive tubes that were driven into the lunar soil, a deep drill, and again, a number of different types of sealed containers, one of which we utilized during the Apollo Next Generation Sample Analysis Program, or ANSA. These are some of the specially collected samples and curated samples, which again provide us with a overarching manner of how potentially one can have these sorts of tools to collect volatile-rich samples at the poles. And we have, as you can see, the far left, a variety of vacuum sealed samples from gas analysis sample containers, special environmental sample containers, to core sample vacuum containers, and they're all of various sizes, but they did have one common feature, and this was this knife edge of stainless steel and this indium seal, in which once the core or the sample went into that container, they could then be sealed on the surface of the moon. There are also special samples that we utilized during the ANSA program, unopened drive tubes. That's one sealed drive tube that you can see in the middle diagrams. And then finally, there were a number of frozen samples. They weren't frozen on the surface of the moon. They were returned and exposed to terrestrial temperatures, but then they were frozen for approximately 50 years in a freezer at the Johnson Space Center. So these all provide us a little bits of lessons learned of how to collect samples during the Artemis program. Also, what's really, really important is being able to curate these samples. And ideally, careful curation has been the key in preserving the longevity of which these samples can be utilized to really re-answer and reveal new secrets from these lunar samples. And again, this is a mandatory step that's, these individual steps are mandatory to preserve those individual samples. And again, for Artemis, this is another lessons learned, that curation and processing and really clean, nitrogen-rich environments is really helpful. So the Apollo sample collection and the missions and the work that's been done on these samples have provided us with some of our most fundamental understanding of the moon, but also the solar system and the Earth-Moon system. For example, lunar rocks have provided information concerning the origin of the Earth-Moon system. It was actually during Apollo 11, the first samples brought back, there was a identification that some of those samples, primarily the coarse-grained plagioclase, provided information with regards to, did the moon go through a primordial differentiation event very early in its history? And then the question following that, do other planetary bodies go through that same differentiation event? There's also a number, as you look at the moon, there's again large basins on the surface of the moon that reflect a number of impact events on the lunar surface. And this led to developing models for the bombardment of the inner solar system. And the moon is one place that record is kept. And also this may provide some information with regards to the dynamics of the outer solar system. The rocks that we've collected, primarily many of those that are the pyroclastic deposits, do suggest there are volatile reservoirs on the moon, and there are volatile cycles both on the lunar surface and in the lunar interior. Some of the regular samples provide us with space surface interactions on an airless planetary body. The remote sensing combined with samples provide us with a better understanding of the thermal magnetic history of the moon. And then, of course, the moon was a starting point for being able to use a wide range of stable isotopes to really identify and fingerprint the building blocks of planets and building blocks in the early solar system. So from Apollo sprung a lot of fundamental concepts that we are currently utilizing and modifying with regards to our understanding of the solar system. With regards to samples and what we learn from samples, one, samples are needed to establish ground truth from orbital data. It's been very, very successful fine-tuning orbital data. Samples are needed for chronology and geochemistry, but not all samples are equal. For example, there are two samples, they're troctolites from Apollo 17, 76535 and 76536. And in a hand specimen, they look similar. The troctolite to your left, a number of chronological measurements have been made on that. It's virtually impossible to do it on the troctolite to your right. So, one question that one can ask is, when you're in the field on the surface of the moon, how can you differentiate these sorts of samples and collect the right one? And I don't have the answer, but that's an answer, a question that needs to be answered. And again, we learned from Apollo, samples are needed from a wide range of lithologies. The more diverse lithologies you have, the better understanding you have of the moon. And then finally, trained humans, trained astronauts on the surface of the planetary body are the best for sampling. They can make decisions with input from the geology back room and the science back room, but it's their understanding and their observations that essentially allow them to go through the decision-making process of selecting the right samples. And also humans are necessary for placing those samples in geological context. I'm just going to show you the image to the bottom right, which is from Harrison Schmidt. Again, this is that little bit of orange soil next to Shorty Crater that I showed you in the first slide. And he has a geological map that we can put those samples within that geological context. Okay, let's go ahead and look at sampling targets for the Artemis mission. As I showed you earlier, most of the, all of the sample return missions on human missions were around the Procellarum Creek terrain. What we're essentially looking for is missions to the South Pole, which is in this area, on the globe to your left, bottom left. And this is a map, these are maps of the iron concentration from orbital data. The South Pole in the middle diagram is shown, and the South Pole is about the place where you see the Malapert Massif located. That's the South Pole and the target for the initial Artemis missions. And you can see it's at a really unique area. It's near or in, which is the southern Farron and North Acidic highland terrain. So some of perhaps the oldest crust on the surface of the moon. And it's adjacent to the South Pole Aitken Basin, one of the largest basins, or the largest basin, recognized basin on the moon. And then there are a number of impact features within the South Pole shown on the two diagrams to your right, which have what are called permanently shadowed regions that preserve volatiles, perhaps water ice, CO2 ice, and a wide range of other volatiles that perhaps could be utilized for human activity in the future. But at the very minimum, scientifically, they're interesting because they possess at least a fingerprint of a volatile record and a volatile process on the surface of the moon. Compared to Apollo, technology has increased considerably with regards to being able to analyze smaller and smaller and smaller samples. This is illustrated here. The TEM at the University of New Mexico, one of the TEMs on the upper left-hand corner, and the diagram below that is a TEM image of some apigamnite and lawrencite, which are volatile elements that occur in a rock called rusty rock, but it allows us to identify and look at the nanometer scale. There's a variety of ion microprobes that allow us to do trace elements, isotopic measurements, stable isotopic measurements on a wide range of materials on the order of 1 or 2 millimeters in size, or microns in size. And then there's a wide range of SEMs and that are equipped with EBSD types of measurements that allow us to better understand, again, on a micron to nanometer scale, the structure of glasses and individual phases in lunar rocks. So again, it's really great that we can look at smaller and smaller and smaller phases. And engineers could just simply ask, boy, why do we need so much material? all we need is if we can just get a thumbnail size sample, we can do all this great stuff with all these very sophisticated instruments. That, and again, one can do that, and this shows, again, two sorts of measurements that these instruments allow us to look at smaller and smaller samples with really high precision. This is some recent calcium isotope measurements and being able to differentiate a wide range of lunar and terrestrial samples with high precision measurements. There is an ion microprobe approach that you can use to date individual zircons. So again, why bring home fist-sized samples or bigger when one can just have these little zircons that one can date? And as the samples get smaller and smaller, I found that some of the analytical tools are getting bigger and bigger and bigger. This is, again, an ICP-MS to the left. I think this is one at the Johnson Space Center. And you can see that, answering the engineering question, well, why can't we make these measurements on the spacecraft? You'll have a hard time putting that on a spacecraft and making those sorts of measurements. Also, this is a beamline to your right, which Carl has a lot of experience. Steve has a lot of experience. These sorts of beamlines, again, you can't really put something like that to generate data on the lunar surface. And then finally, another aspect, again, I put these buts that keep making things smaller, and the need for returning these samples is that the small samples aren't always representative. For example, if one had a sample like that norite up there, it's orthopyroxene plus plagioclase. If you only had a sample that big, you would again say that's a norite, and that it was probably different from the dunite that's below it, which is again really different from the anorthosite, which is right there. But they're actually all part of the same sample, which is a troctolite. So again, when one is looking at things with a smaller and smaller perspective, which opens up lots of other doors, one should always be aware of the sample and geological context that one is placing those materials in. Also, this illustrates again with regards to a matter of scale and mass. This illustrates calculation that Lars Borg and I did in 2006 for flare and anorthosite, a norite in the middle, and a Mare basalt 15475 to the far right. And in order to make measurements, argon, rubidium, strontium, samarium, neodymium, initial hafnium, epsilon, neodymium 142, those are the sample masses that one needs to make those sorts of measurements. And so those are partially dictating, if one wants to do chronology, those are the sorts of masses that one would need for those different lithologies. And again, that's for making those isotopic measurements. If one wants to do more with that rock, one needs, again, larger samples. Also, there's probably a diversity of samples at the South Pole, and that one is going to be returning. This includes regolith with varying degrees of maturity, probably primordial lunar crust, which could be very extremely important. There may be some basalts that were transported maybe from the South Pole from the Procellarum Creek terrain. There's a variety of impact-produced rocks that could be remnants of this South Pole Lake Basin impact event and other impact events in the South Pole. And then there are other sample types, like I mentioned before, very volatile rich samples that occur in these cold traps. Let's just go through each of these a little bit at a time. Just illustrates, the types of regolith that one could collect. Some of these can be scooped. As you see, there's a bag of regolith in the upper right. Some of these can be cored, and those cores over to look at the stratigraphy. Both are important. One gets a view of surface processes with the scoop samples at the surface, and then core samples gives you a better understanding of the stratigraphy of the regolith from those locations. There are a variety of information that one can extract from the regolith in terms of grain size, composition, maturity, and also one can extract lithic fragments from the regolith that one can better understand, and again, increase the diversity of materials that one is really looking at. And again, for Tony, obviously Tony is doing oxygen isotopes on this, trying to reconstruct the impact target, the impactor, and other processes taking place in the near surface lunar environment. During Apollo, as I mentioned, there's evolving steps with regards to activities on the lunar surface. There also were evolving tools in which this illustrates the left-hand side, the types of cores that were utilized with varying degrees of efficiency from Apollo 11 to 15 and 17. And the 15 and 17 core tubes were probably the most successful of all the cores that were taken on lunar surface. This is from a paper, the diagram to your right. Part of it was taken from a paper from that Zach Sharp and Julie Stover and I put together. And this illustrates some of the temperatures that one expects in these cold traps. And so how does one collect those? If one uses a core that one did with Apollo and tries to hammer that into really cold regolith, that's at 50 degrees K, or it has some abundant ice in it. How does one collect that? How does one not only collect it, but also preserve it at those sorts of temperatures? And I think kind of the answer is, at least right now, and there's a survey team looking at this right now, is that from Artemis 3 forward, you do the return of these samples in evolutionary steps. For example, for Artemis 3, what do you do first? You essentially have boots on the ground to look at the characteristics of these cold traps at the surface. Also, you get a better understanding of the real temperatures, the distribution of temperatures. Then perhaps you do some surface sampling and put them into these sealed containers and put a lid on it. And then again, have the understanding that that's going to warm up to room temperature, but one can still do analyses of those gases. The next step is obviously what one can do is, now that you have a better understanding of the conditions at which these environments occur, one can do a step-by-step improvement and developing of a strategy to go from collecting samples at room temperature to perhaps eventually collecting samples and preserving them at 50 degrees to 75 degrees K. Those are big, not only scientific steps and technology steps, but they're also big investments in time and cost. And so starting small and building to the future allows you to better understand what science payoffs and what are the environments that you're going to be investigating on these types of samples. And again, I couldn't help but show this. This is some work that, again, we did on CASA, where we took one of these core sample vacuum containers, extracted the gas, and what you'll see in that little image to the bottom right is a picture of Zach Sharp, and he was actually the first one ever to analyze one of these apparently preserved lunar volatile samples. So this was great that we did it at UNM. Also, there are a wide range of ferronorthocytes that are associated with the southern ferronorthosite highland terrain. The ferronorthocytes, do occur in a number of places, as you can see on the image to the upper left, that shows the little yellow spots are locations where there is plagioclase-rich rocks. The diagram to the upper left also shows crustal thicknesses. And the area that we're going to, that's at the bottom on the diagram to your left, bottom left, there are potentially some substantial amounts of ferronorthocytes there. Are these northocytes all flotation cumulates? And do they better allow us to better understand the initial differentiation of the moon? Or are these different rocks than what we collected primarily from Apollo 16, which has abundant ferronorthocytes in the sample collection? And then we have a wide range of breccias that have been really important from Apollo. And I think there'll be similar sorts of lithologies collected from the South Pole. You can see 14,445, and that is about 6 centimeters across with a number of lithic fragments or clasts in them. Boulder 2 at Station 2 of Apollo 17. This is primarily materials that could be derived from the lunar mantle or magnesium sweet sorts of rocks. Those are dunites. And then finally, we have another breccia, that 14321, that contains some of the oldest Mare basalts from the surface of the moon. These sorts of lithologies, these sorts of breccias, offer a wide range of materials within them. And as you can see, one can't collect a small breccia. One has to collect a fairly large one on this scale to better examine the class that may occur in them. And then, as I mentioned, Steve Simon has done a lot of work on these rake samples and small samples collected in the 73001 2 core. And as you can see, the tongs of the rake can be adjusted to select a wide range of different sizes. And so that brings us to, well, we learned a lot from Apollo. What can we learn more from going to the South Pole? And this diagram is just meant to illustrate some of the more deeper questions that one can ask with a well thought out sampling strategy from the SPA. One, we can get a much better understanding of the chronology and evolution of the primordial lunar crust. How did the crust form and evolve? And what is the origin for the crustal heterogeneities that we see all through the moon? Obviously, in these particular cold traps, these are areas that we did sample all from Apollo and their unique environments. The age of the South Pole Lake and Basin, there were a number of robotic missions that I was involved in. None of them were funded by NASA, but this allows us, this is one of the oldest and biggest impact basins on the surface of the moon. So dating this event will allow us to better understand, reconstruct the impact history of the moon and the inner solar system, and maybe help us better understand the dynamics of the outer solar system. And then finally, during Apollo, there isn't any well-recognized mantle samples from the Apollo horizon, from the Apollo samples. And so the excavation by the SPA event, the South Polacan Basin event, may have excavated lunar mantle in addition to deep crust, allowing us to better understand the nature of the lunar mantle, let's say symmetry, its composition, and linking that to any sort of early magma ocean differentiation processes. So the last couple slides I just wanted to show right now, and these are kind of answers to some of these questions. Again, why do we need to collect samples? Aren't rocks all the same? And again, the short answer here is, like the Earth, the moon has a wide range of diversity, and each individual sample allows us to better understand the evolution and origin of the moon. And then why do we need to return samples that we can do? Why can we do with return samples that we can't do by making those measurements on the moon? And again, as I showed earlier, to interrogate these samples, to get as much out of these as you can, you need the samples in the lab. And what's really important also in the lab is, we've had Apollo samples for 50 years, and techniques have evolved and gotten better, and new questions are constantly asked about the moon and its place in the solar system. And so having samples that you can just say, well, these are well curated, we can go to curation and get some new samples because we have these new techniques. We have chlorine isotopes we can do that we couldn't do. We have nanosims measurements of examining zircons at a really tiny scale. We can do that now. We couldn't do it during Apollo. So that's why it's so important to have those samples back. How much sample do we need to collect? Most geologists will say as much as you can bring back. I know most of you have done field work, and you sometimes go out and collect more samples than you'll ever look at, but very often there are a number of samples that, this is the sample that answers all the questions, or at least the questions I have. So it's really, again, important to understand the question I'm asking, and also in terms of size. As I showed you, some of these large breccias really do have a lot of other lithologies that one can essentially look at and utilize, and we're actually doing that now with CASA Moon. And can I scoop the sample off the top, or do I need a drill down to collect them? It's important to do both. Do we need humans to collect samples, or can rovers do it as well? And again, I think humans, as I mentioned earlier, can better place samples within a local geological context that then can be expanded from orbital data, and that the decision-making process when you have boots on the ground may be a little bit different than if you're in the back room directing a rover. And then, rovers do provide, for longer sojourns, like we have a mission that may go across the whole South Polacan Basin. You couldn't do that with humans. Also, there are areas that may be of high risk. Perhaps you need a rover to go into some of these permanently shadowed regions to collect samples because they're so cold. And do we have to transport and store the samples in some special way? Yes, We want to keep them away from the Earth's atmosphere where they can have an impact. And in some cases, we also want to make sure that eventually we have the capability of returning them at temperatures and maybe vacuum conditions of the lunar environment. So that's all I had for today. And I just wanted to thank everybody online and everybody here for joining us. And again, I just wanted to mention that this is every week for the rest of the semester. And just as one more headline is that we are at the University of New Mexico going to host the NASA Exploration Science Forum in 2025, July 22nd to 24th. And again, everybody that's online, whether you're funded by Survey or not, you are invited to come. It'll be a fun time in Albuquerque in July. So please come. That's all I had. Thank you all. Yeah, I just had questions.
I have a comment and a question.
Yeah.
The comment is to everyone online and here. We analyzed the ANXA drive tube. It was opened in a nitrogen atmosphere. We sampled it in a nitrogen atmosphere and we analyzed it for hydrogen isotope composition in our system. It's never been exposed to the Earth's atmosphere. And to my knowledge, it's the only sample that we've ever analyzed and that may exist on this planet that does not have contaminated water. From putting anything in the air, it's going to get a coating of water on it. And we always degas the samples to get rid of the water. With these samples from the core, there was no water. It was just incredible to see.
Yeah.
So yeah, careful curation and storage and collection on the moon allows us to do things that we couldn't.
Yeah,
do.
and it's really important with regards to curation. I know Paul Lucy from the University of Hawaii did this at the Johnson Space Center after we processed the whole sample that was in the sealed core sample vacuum container. He essentially brought a camera that he had into the nitrogen glove box. And he essentially made measurements of the hydrogen concentration on that surface and found nothing. So that was kind of important, and it again substantiates what you were saying, Sam. But what one has to be careful of, he noted that over the period of time that the camera was in that box, the glove box, he had hydrogen coming from the camera itself and adhering to the core. So it's amazing how, the smallest little thing can really screw things up royally. And that one really always have to pay attention to potential sources of contamination. I know that also, we were processing some of these samples and placing samples within bags and then sealing them, triply sealing them. And there was a little bit of fluorine that came off of that heating process, and that essentially landed on some material. And again, a very, very tiny thin coat on the order of nanometers in thickness. But again, it's something that one has to always be concerned about. Do I have any questions online?
Chip, this is Lars. Can you hear me?
Yeah, we can.
I have a question regarding, or I guess I seek your thoughts. When we go through and we look at the Apollo collection and we try and find them for specific measurements, what the common observation is that most of the samples are not appropriate for the measurement that you want to do. And of course, I'm thinking about this solely from a geochronology perspective, but this applies to a lot of other things. And so a lot of the materials that were brought back just haven't proven to be that useful. And so how do you develop a sample strategy that, maximizes the scientific yield out of the samples, given the constraints that are placed on astronauts and robotics and things like that for sample selection. Because we did this calculation. Well, all you need is this amount of ferrone and orthosite and this amount of norite and this amount of what have you. But there's an assumption in all that that you've got the perfect rock, and most
That's right.
of them, excuse me, most of them aren't perfect. So how do you account for all this in these estimations and this development of sampling strategies?
Well, one, Lars, I think one has to remember that during Apollo, we were there for the first time, and we really didn't know what worked in terms of what were the important samples, what were the important samples. So again, I think the astronauts and the science team were a little bit handicapped because, it was the first time. We didn't know it was there. We wanted to collect everything we could, and we didn't know what would work and what wouldn't. Now I think we have a better understanding of at least what some of the science should be, probably more than the Apollo did. And maybe that partially can guide us. But, we still have this dilemma, as you pointed out, and you pointed me to these two samples, those two troctolites from Apollo 17. One was, everybody does chronology on, one of the troctolites, because you can make a lot of different measurements. The measurements, if you do them properly, make sense. But this other one, the other troctolite from Apollo 17, again, I think it was from the same station, just is useless. And so, we're probably going to need people like you and other individuals who realize that there are issues like that in sample selection. And at least right now, if you ask me, I don't know if we had astronauts going to that site and we saw those two samples on the surface, I would have said pick them both up just in case. But I think that's a strategy that one needs to develop in terms of, what are the good rocks for chronology. And again, there are other measurements beside chronology, obviously.
Yeah, I mean, I come at it from a chronology perspective, but pseudophile elements are another one and things like that. But maybe some strategy to actually go and examine the samples in the Apollo collection that have proven to be the most useful for, general science and see if they share any common characteristics.
Mhm.
But there's also another component with Apollo collections is that most people don't know what's in there. And so
Yeah.
they tend to analyze the same, 25 samples because that's all they're familiar with, because that's all that's in the compendium. And
Yeah.
there's also a lack of knowledge of the collection, which may bias that. Okay, but
Yeah.
thank you for your thoughts.
Well, I had just one other comment. Again, coming up with a strategy that, again, you could differentiate one of these troctolites from the other, but the norite that you and I have worked on from Apollo 17, I probably would have discouraged the astronauts from picking that up because it looked like it was so shocked. But yet that has been giving you and the work you've done with the zircons really pretty fantastic numbers.
Yeah, well, it's always that way, right? I mean, we're all geologists. We all go out in the field and every field season, you end up with your favorite rock. And the odds are you probably didn't pick that on purpose. It just turned out to be your favorite rock after you analyzed it. And so, you're right. There's a certain unpredictability in the whole thing, but at the same time, if looking for those, kind of Rosetta Stone like rocks is the key thing, some criteria, should be established and maybe not strictly enforced during collection, but it should at least be explored somehow.
And actually, in my conversations with Jake Bleacher at headquarters, he was mentioning that it would be nice to be able to develop a strategy primarily for chronology that one can determine and select the right samples. And maybe that's just an impossible task. I don't know.
Yeah, I don't either, but the point is that chronology is so sample intensive and has such high requirements that if it works for chronology, it probably will work for other things too.
Yeah.
And I think that's the critical thing. It's not just chronology that should drive this. It should be everything. But yeah. Well,
All right. Well, thanks, Lars.
Yeah, if I could chime in. Hi, Chip.
Hi. Hey, who's
Um,
this?
Steve.
Oh, okay, Steve.
I can turn my video on. Let's see. Hello. Hey, Lars, I think one pathway to answer your question is that the technology we now can bring to bear as far as in-field analyses, right? Handheld XRFs, XRDs, which are being, put to good use, on like the Mars rovers and stuff. So I think one possible answer for you is the more high grading we can do on the moon with these technologies that were not available in the 70s. I mean, you can do a lot. There's a small SEM on the space station that could be brought to the moon's surface. It's about this big. That could be huge as far as high grading. You could have a strategy of collecting large amounts of sample and then having the astronauts high grade it, or even collect the data and send it to the geochronologists, and they say we want that one. So I think there's a real advantage that we have in integrating that analyses on the moon to get the right samples.
No, I agree, and those are very good points. The question though is that, excuse me, I have a little bit of a cold. If you're making a measurement, you still have to have some criteria.
Yeah.
Just getting a rare earth element pattern or something doesn't necessarily mean it's going to be a perfect rock for siderophile elements or chronology or whatever your high bar is. So you have to tie these measurements in with something, I presume, in the sample collection to establish some measurable criteria that gives you confidence that it's going to allow some other technique to be applied with success. But your point is very well made, and yeah, thanks for pointing that out.
And I think there's a path forward, right? In that, like you say, there we have the Apollo lunar collections. If we had a candidate suite of instruments that could be deployed on the moon in a lunar base, that the astronauts could use, you could then basically use those tools on the Apollo collection to say, which one of these are like establish some criteria using plausible equipment that the astronauts could have on the moon. I think it could be an interesting.
Yeah, guys, we need to close down our discussions now. I'm sorry. But one thing that we should do, Lars and Steve and a number of people online, you will be at the next NASA Exploration Science Forum. Perhaps we need to have a special session, just an afternoon that focuses upon the early evolution of the moon and how do we sample and better understand it with Artemis, something along those lines. I know Survey usually doesn't do special sessions, but we're having it here, so we can do what I want.
I think that's a great idea, Chip.
Yeah,
Thanks.
well, thanks, guys.